Liquid-liquid extraction is a technique that can be used to isolate a compound from a mixture based on the differential solubility of that compound that's displayed between two immiscible solvents. The two immiscible solvents are usually a pair of a polar solvent and a nonpolar solvent. And usually polar compounds will be more soluble in polar solvents, while nonpolar compounds will be more soluble in nonpolar solvents. The distribution of a compound between an organic solvent that is usually going to be nonpolar and an aqueous solvent which is polar can be described by the distribution coefficient. It is a ratio of a particular compound's solubility in an organic solvent versus its solubility in an aqueous solvent. So we're showing here the distribution of this red compound between an organic layer and an aqueous layer. If this distribution coefficient Kd is less than 1, that means the lower part of this equation has a larger number, which results a Kd value less than 1. When we have a Kd value less than 1, it means that compound has a higher solubility in aqueous solutions. If Kd is equal to 1, that means this compound is equally soluble in aqueous as well as the organic layer. If the Kd value is greater than 1, that means the solubility of this compound in the organic layer is much higher than its solubility in water. So by taking advantage of these different solubilities of a solute in a pair of immiscible solvents, we can selectively transport compounds from one liquid phase to another during extraction, and use this to isolate compounds from a mixture of compounds. Properties of solvents suitable for extraction. Obviously, one of the solvent pairs would be a polar solvent like water, which will consist the aqueous layer. And the organic layer should be made of an organic solvent which is relatively nonpolar and immiscible with the aqueous solvents. And also, it should have a large range of solubility for a large number of organic compounds. And especially, it should also have a low boiling point. So the boiling point is when the solvent changes state from liquid to gas, and this boiling point is low means that this solution boils at a very low temperature, so we can remove it very quickly by heating at a low temperature. This is important, and you will see how this comes into use in the later slides. Some examples for organic solvents suitable for extraction are diethyl ether, ethyl acetate, dichloromethane, and hexane. When we have these solvents mixed together, how do we decide which layer would be in the top and which layer would be in the bottom? It will depend on the density of the solvents. So the solvent that has a higher density will be the bottom layer, and the solvent with a lower density will be on top. Usually, often, the aqueous layer is the bottom layer, and the organic layer is the top layer. But whenever we use dichloromethane as our organic solvent, then the organic layer will be the bottom layer because dichloromethane is heavier than water. In those cases, the aqueous layer will be in the top. So we decide which layer is going to be on the top based on the density of these solvents. What if we did not have information about the density of the solvents and we had to figure out which layer is the organic layer and which layer is the aqueous layer? We would do something called the water drop test, which is basically adding a few drops of water, and we observe which layer this water would join to. So the water will obviously join to the aqueous layer, so the aqueous layer will grow in size, and we can therefore conclude, okay, the bottom layer is the aqueous layer in this case, and the top layer is the organic layer. So whenever you get a question where you're told that you don't know the densities of these solvents, how would you determine which layer is in the top and the bottom? You would do a water drop test. Here I'm going to explain the general procedure of a liquid-liquid extraction. We would usually start with the mixture of compounds. So in this example, we have two different compounds mixed together. We start off with dissolving them in an organic solvent. So the solvent would have a large range of solubility and is able to solubilize both of these compounds in the solution. Next, we're going to introduce an aqueous solvent. So either one of these compounds would have a higher affinity towards the aqueous solution. That means its Kd is less than 1. Then it will move from the organic layer to the aqueous layer. Or else we might be able to convert one of these compounds into a more water-soluble form by reacting it with an acid or a base. So then that compound will become more water soluble and it will move to the aqueous layer. So you can see by this step we have an aqueous layer and an organic layer, and one of the compounds have been converted into a more water soluble form. So it's now moved from the organic layer into the aqueous layer, and the other compound is left in the organic layer. Then by separating these two layers, now we have separated these two compounds from the initial mixture. And in order to isolate these compounds, the next steps involve removing the solvent and separating these compounds. The general procedure to isolate the compound from an organic layer usually follows these steps. Even after removing the aqueous layer, there's always going to be some droplets of aqueous layer trapped in the organic layer. So in an attempt to remove those droplets, we would wash the organic layer with some water. So like dissolves in like, so when we're mixing with water, those water droplets that were trapped in the organic layer are going to be drawn away to the water layer. And by removing this water layer, we're going to remove that water droplets. But there still could be some traces of water left. To remove that, we can wash the organic layer with saturated sodium chloride. So it's basically a very saturated salt solution. Because it's very saturated, it can absorb water really well. So if there were any more traces of water left, that will be absorbed into this salt layer. And as the further step, drying step, we can add anhydrous sodium sulfate. So sodium sulfate is also a salt, and this word anhydrous means that it's very dry, it's devoid of any moisture, so it's able to absorb moisture really well. So if we add some of the solid into the mix with it mix it with this organic layer and let it sit for a while, if there were any more traces of water left in the organic layer, will be absorbed by this salt. So all of these steps that I mentioned here were involved in removing water from the organic layer. So removing water from organic layer. So all of these steps were basically for that purpose, and we also call this as drying the organic layer. Drying in the sense that we're drying it of water, removing water. After this organic layer is fully dried of water, that is, all the water has been eliminated, then we can filter it through a filter pipette and collect it in a fresh vial. The reason we filter it is because to avoid any of these solid particles moving along with it. Once we have the organic layer filtered, then we're going to evaporate the organic solvent. And here is why it was important to have a low boiling point for the organic solvent. We can evaporate it really fast by heating it to a very low temperature, which is much lower than the melting points of these compounds. So these compounds are not going to be affected. The solvent will be quickly removed and our compound will be remaining as a residue, and by that we're able to isolate our compound. And all of these drying steps are very important because if we had any traces of water left in this organic layer, it's going to take a long time for this to evaporate because water boils at 100 degrees Celsius. That means if there's any water mixed, we are going to need to heat it to a much higher temperature in order to evaporate the organic solvent, and that higher temperature might affect the state of our compounds, which is why we do some of these drying steps to get rid of water in the organic solvent. Now we're looking at the general procedure to isolate the compound that was in the aqueous layer. So if we had made this compound water soluble by following a chemical reaction, if we had added an acid in the beginning to make this water soluble, now we would add a base to reverse that reaction. If we had added a base in the beginning to convert this compound to a water soluble format, now we would add an acid to reverse that reaction. So when we reverse the reaction, this compound is reverted to a water insoluble form as it was in the beginning. So it's going to precipitate out of the aqueous solution. And then we can do vacuum filtration to separate the solids from the solution, and we can dry it, and now we simply have the isolated compound. Now let's look at how that general extraction procedure is used in today's experiment, where we are trying to extract 9-fluorine and benzoic acid from each other when they are in a mixture. So in the beginning, we have this mixture of benzoic acid and 9-fluorine. So 9-fluorine is yellow, colored here, and benzoic acid is shown in green. Benzoic acid is actually white, but I'm using green, so it's more visual. But 9-fluorine actually has a yellow color to it. First of all, we start with dissolving both of these in a common organic solvent, and in this case we're going to use diethyl ether. Now they're both soluble, so we have to do something to convert one of these compounds into a more water-soluble format. When we look at the structures of these compounds, the preferable compound for that kind of reaction is benzoic acid because it has this carboxylic group and it's an acid, so it could be reacted with a base. That is why we are adding 5% sodium hydroxide aqueous solution here. So now a chemical reaction happens where the benzoic acid reacts with sodium hydroxide in order to produce sodium benzoate and water. And you can see sodium benzoate has some charge groups, which makes this an ionic molecule, and ionic molecules are able to form ion dipole interactions with water molecules, so it's going to move from the organic layer into the aqueous layer. So this is how we're going to force all of the benzoic acid from the organic layer into the aqueous layer. We will wash the organic layer a couple more times with the sodium hydroxide solution to make sure all of the benzoic acid is converted into sodium benzoate, and therefore they will all move into the aqueous layer. Now the two different compounds are in two different layers, so we're going to separate the organic layer and the aqueous layer. And the next steps are going to be to isolate the compound out of this solution. Now we will be trying to isolate the 9-fluoronine from the organic layer. So what we have here is the 9-fluoronine dissolved in diethyl ether. That was the organic solvent that we added in the beginning. And there can be some water droplets trapped in this organic layer as well. So we're going to follow a couple of the drying steps that I described earlier. One of them is we will wash the organic layer with saturated sodium chloride solution, and we try to draw out any water droplets trapped in the organic layer to the aqueous layer, and then we remove the aqueous layer, and as a further drying step, we are going to add anhydrous sodium sulfate to this solution and let it sit for a while to make sure any other remaining traces of water is absorbed by the sodium sulfate salt. Next, we're going to filter the organic layer through this filter pipette and collect it into a fresh vial. And we add a boiling chip. And the purpose of the boiling chip is to prevent any aggressive bubbling when the solution is evaporating. So it prevents the solution from splashing around everywhere. We're going to heat it to a very low temperature. The boiling point of diethyl ether is very low, so it's quickly going to evaporate within a few minutes, and we will have the 9-fluorinone isolated at the bottom of the vial. So probably when all of the diethyl ether has evaporated, there'll be a little bit of liquid left, which is soluble 9-fluorinone. And once we remove it from the heat, it's quickly going to solidify, and we will be able to isolate 9-fluorinone. Now, in order to isolate the benzoic acid from the aqueous layer, what we do first is, since what's currently soluble here in the aqueous layer is actually sodium benzoate, we have to convert it back to benzoic acid. That's the compound that we originally started with, and we want to isolate that. To change sodium benzoate back into benzoic acid, we're going to add 6 molar HCl. That will react with sodium benzoate and convert it back to benzoic acid, and we will get sodium chloride as a side product. Since benzoic acid is insoluble in water at room temperature, it's going to precipitate, and we will be able to collect that precipitate through vacuum filtration, and then we can air dry, and now we have the isolated benzoic acid. Down here is just an example of how the filtration system is going to be set up. So in this picture, there's a Buchner funnel, but we sometimes use that funnel or the Hirsch funnel, the top picture here. It could be either one of those, fixed to the vacuum flask, and there is an outlet that we connect with a rubber tube to the vacuum connection. So that will help us quickly filter this precipitate and remove all the solution using vacuum filtration. To determine the success of your extraction procedure, you can calculate the percent recovery for each of the two compounds. So you can calculate the percent recovery for benzoic acid and the percent recovery for 9-fluorinone. You get that by dividing the post-extraction weight by the initial weight times 100 in order to get the percent recovery for each of these compounds. And if you have a good percent recovery, that means that you were very good at the technique of extraction and you had very little loss of product. However, the percent recovery itself will not tell us whether those extracted samples were pure or not. So to test the purity of each of the extracted samples, we will be following a thin layer chromatography experiment where we will spot each of the extracted samples and the initial mixture on a TLC plate and develop it to observe the purity of our extraction. So what we do is we have the initial mixture, which is the mixture of benzoic acid and 9-fluorinene. B is the sample that we have extracted by isolating the organic layer, and it should be 9-fluorinene. C is the sample that we have isolated by extracting the aqueous layer, and that should be benzoic acid. Each of these solids are dissolved in a small amount of ethyl acetate, which is also a versatile organic solvent that can dissolve both of these compounds. And we will spot them on the TLC plate, and we will develop it in a solvent system that is made of 10% ethyl acetate and 90% hexane. So you can see that the solvent system is mostly a nonpolar solvent system. And out of the two compounds that we're comparing, looking at the structures, we know that 9-fluorinene is going to be 9-fluorinene is the more nonpolar out of the two. So we expect 9-fluorinene to move further up on the TLC plate compared to benzoic acid. In the first sample, which is the mixture, we expect to see two spots. The lower spot would be corresponding to benzoic acid, and the top spot would be corresponding to 9-fluorinene. The extraction from the organic layer, we ideally expect it all to be 9-fluorinene only. So in that case, we should just see one spot which aligns with 9-fluorinene from the mixture. And the extraction from the aqueous layer should ideally only contain benzoic acid. That means we should see a spot, one spot in it that corresponds with the lower spot from the initial mixture. You would calculate the RF values for each of these and you can make a comparison, and in your conclusion you can say, based on these results, we can say that our extraction was successful. And the alternate results would be you would have some contamination in each of these samples. Usually it's the aqueous layer extraction that gets a little bit contaminated with some 9-fluoroenone, because when we draw out the aqueous layer, it is sometimes difficult to avoid drawing out some of the organic layer as well. And this will become more efficient when you practice doing the extraction, having hands-on experience. When you do it many times, you get better at it. But if you're doing it for the first time, you should expect to see a little bit of 9-fluoroenone contaminating your aqueous layer extraction. So this is all that I had to discuss for the extraction lab. And I will be having my office hours as usual on Friday. Please stop by if you have any questions. It will be from 8:30 a.m. to 10:30 a.m. on Friday by WebEx, and I will post the link on Canvas. If you can't make it to that time, and if you have questions, please reach out to me through email so I can respond to you as soon as possible. Thank you.